In July 2025, an automated telescope sitting in the Chilean desert flagged something unusual, a point of light moving at the wrong speed, on the wrong trajectory. The software marked it as suspicious and sent an alert to the duty astronomer on shift. He looked at the data, ran the numbers again, looked one more time, and realized he was looking at something that had no business being in our solar system at all. It was a comet, but not ours. It had come from somewhere beyond the edge of the solar system, traveling at roughly 60 kilometers per second, faster than any object that simply orbited our sun could ever move. Its path was open, hyperbolic. It was not going in circles, it was passing straight through. Within a few months, it would swing around the sun and leave again, back into the darkness between stars, back to wherever it came from. They named it 3I Atlas, the third interstellar object humanity had ever seen. In the entire history of astronomy, across hundreds of years of sky surveys, millions of cataloged objects, we have caught visitors from another star system exactly 3 times. The first was Oumuamua in 2017, a strange elongated object with no tail, behaving as though something was pushing it from the inside. Scientists still argue about what it was. The second was Borisov in 2019, calmer, more familiar, looking like an ordinary comet that had simply wandered in from somewhere far away. And now, the third. And the third one broke something. Not a telescope, not a theory. Something more fundamental than that. When scientists finally managed to study what 3I Atlas was actually made of, they found water. That part was expected. Comets are essentially frozen, dirty snowballs. They carry water the way old houses carry dust. Everywhere, in everything. But the water inside 3I Atlas was not the water anyone expected to find. It was wrong, measurably, undeniably, profoundly wrong. To understand why that matters, you need to know one thing about water. Not all water is the same. The water molecule you drink is H2O, 2 hydrogen atoms, 1 oxygen. But hydrogen comes in different forms. Most hydrogen atoms are simple, just a proton at the center. Some, however, carry an extra neutron alongside that proton. This heavier version is called deuterium, and the water it forms is called heavy water, or HDO. It exists in ordinary water too, in tiny amounts. In Earth's oceans, roughly 1 water molecule in every 6,400 is the heavy kind. In the comets of our solar system, the ratio is similar, hovering in the same general neighborhood that planetary scientists have come to think of as normal. 3I Atlas was carrying 40 times that amount. Let that settle for a moment. Not 40% more, not twice as much. 40 times the concentration of heavy water found in Earth's oceans, and 30 times what we see in our own comets. Luis Eduardo Salazar Manzano, a doctoral candidate at the University of Michigan who led the team that made the measurement, described it simply. The amount of deuterium relative to ordinary hydrogen in the water of 3I Atlas is higher than anything we have ever seen before. In any comet, in any planetary system we have ever studied. The measurement itself was made under extraordinary conditions. 6 days after the comet made its closest pass to the Sun, researchers turned the Atacama Large Millimeter Array, ALMA, one of the most powerful radio telescopes on the planet, towards the comet's coma, the glowing cloud of gas and dust surrounding its nucleus. ALMA is one of the few telescopes capable of pointing close enough to the Sun to catch a comet at this stage of its journey. What they detected in that cloud were the unmistakable chemical signatures of heavy water and methanol. Ordinary water was too faint to measure directly, but the heavy water was there, loud and clear, announcing something about where this object had come from. Because deuterium is not random, it is a fingerprint. The chemical processes that concentrate heavy water into ice require extreme cold. Not cold like Antarctica. Not cold like the outer planets. cold like nothing in our solar system has been for billions of years. Below 30 Kelvin, which is roughly minus 406 degrees Fahrenheit, the kind of temperature that exists in the deepest reaches of interstellar molecular clouds, in the dark spaces between star systems where light from any sun barely reaches. For 3I Atlas to contain this much heavy water, it must have formed in a place colder than anything our sun has ever created around itself. A planetary system fundamentally different from ours. A colder, darker, stranger place than the one that built the Earth you are standing on. The comet has been traveling ever since, and here's the part that does something odd to your sense of time when you first hear it. 3I Atlas is estimated to be somewhere between 3 and 12 billion years old. Our solar system itself is only 4.6 billion years old, which means this object may have been drifting between the stars for longer than the sun has existed. It formed somewhere in some planetary system, around some star, before our star had even ignited. It got ejected, probably by the gravitational chaos of planets forming and rearranging themselves, which is a violent process. The kind of process that throws enormous objects out into interstellar space like stones from a sling. And then it drifted. For billions of years, through the cold and the dark and the silence between stars. Until last July, when it happened to pass through here. That word, happened, is doing a lot of work in that sentence. Because one of the things this discovery quietly confirms is just how common these objects probably are. We have only seen 3 interstellar visitors in all of recorded history, but that almost certainly says more about the limits of our telescopes than about the actual population out there. The Vera C. Rubin Observatory in Chile, which came online in 2025, is expected to find interstellar objects with far greater frequency as its survey of the sky matures. We may be on the edge of a period where catching these visitors goes from a once-in-a-decade event to something almost routine. But here is what makes 3I Atlas different from what we are likely to find next. Most interstellar visitors will pass through unexamined, too faint, too fast, detected too late. This one arrived at exactly the right moment, while the right instruments were pointed at the right part of the sky, giving researchers a window long enough to actually study what it was carrying. The measurement published in Nature Astronomy in April 2026 is the first chemical fingerprint ever taken of water in an interstellar object. Not the first guess, not the first approximation, the first real measurement. And the first measurement told us something nobody had expected to hear. The conditions that made our solar system are not universal. That sounds almost abstract until you think about what it actually means. For decades, scientists studying the origin of life have worked from a quiet assumption that water is water, more or less, that the building blocks of life that formed here are probably similar to what formed everywhere else that life might exist. The chemistry of our solar system has been the default template, the thing we implicitly measured other systems against. 3I Atlas just showed us one data point that sits completely outside that template. The star system this comet came from was colder than ours. The chemistry was different. The ratios were different. We do not know what formed there. We do not know if it still exists, or if the star it orbited has long since burned out. We have no way to point a telescope at its origin and look, because we do not know where it came from. All we have is the comet itself, and the chemical message it carried across billions of years and light years of empty space. A message written in the atomic structure of its ice before our sun existed, preserved through an unimaginable journey, and finally decoded 6 days after it swung around a star it had never visited before. The comet is gone now. It began its exit from the solar system in December 2025, heading back out into the dark. Astronomers tracked it for as long as they could. It is still out there, somewhere beyond the outer planets, slowing slightly under the sun's gravity before it finally escapes entirely and resumes its journey through the galaxy. In a few thousand years, it will be so far away that no instrument we could conceivably build would ever detect it again. In a few billion years, assuming nothing stops it, it will still be moving. What it left behind is a question. Actually, several questions. And not the kind that come with clean answers attached. If the chemistry of other planetary systems can differ this dramatically from ours, what does that mean for the water on worlds orbiting other stars? What does it mean for the molecules we have been assuming are the precursors to life? If a comet from a colder, stranger system carried water this different from ours, what else might it have been carrying? And how many of these objects are passing through our solar system right now, undetected, carrying chemical records of planetary systems we have never seen and may never find? Those questions are not rhetorical. They are active research problems that a single comet, spotted almost by accident by an automated telescope in a desert, has handed to an entire generation of planetary scientists. One doctoral student, one radio telescope, 6 days after closest approach, and what they found completely changed what we thought we knew about water, about where it comes from, about how different the universe is, even in the places we thought we understood, and maybe, quietly, about whether the chemistry that made us is as common out there as we hoped it was, or whether we are something stranger and more specific than we ever allowed ourselves to consider. 3i Atlas is gone, but the question it carried is still here, and we are only just beginning to understand what it was asking.